Hi, today we're going to talk about the action potential of the cardiac contractile cells. Okay, so we're going to talk about the action potential of the cardiac contractile cells. So you'll also hear them called myocardial contractile cells, and the word myocardial simply means relating to the tissue of the heart. The contractile cells make up about 99% of the cells in the atria and the ventricles of the heart. The contractile cells conduct the impulses and therefore are responsible for pumping the blood throughout the body. So the anatomy of these contractile cells relies on the pacemaker, or they're also called the autorhythmic cells for the action potential. So the pacemaker, autorhythmic, or non-contractile cells make up the other 1% of the cells. So we cannot look at one without knowing what the other is. So they both have ion transport channels, but they differ. So the gap junctions link the two types together, and they also link the contractile cells to the contractile cells. So let's think about that again. The gap junctions link the two types together, but they also link the contractile to the contractile cells. So the sarcoplasmic reticulum stores the calcium channels for the flow of calcium within the cell. It's important to note some of the physiology about the pacemaker cells that make up the 1%. The pacemaker cells are smaller than the contractile cells, and they do not contain myofibrils, no organized sarcomere structure, and they do not contribute to the contractile force of the heart. However, in the contractile cells, the myofilaments are contractile units in the cardiac muscle cell. So the main function of the contraction in the cardiac cell is to pump oxygen-rich blood throughout the body. The non-contractile cells are in the SA node, the AV node, the bundle of His, and the Purkinje fibers. So let's look at the slide and see where these are at in the heart. The SA node is in the right atrium. That's up on the top. This is where the electrical impulses will generate the action potential for the contraction. Okay, when it excites the right atrium, it will also excite the left atrium as it moves through the Bachmann's bundle. You can see it move across in yellow to the left through the Bachmann's bundle. The electrical impulse will then travel down the bundle of His through the fibers. The specialty of these fibers is the fact that they are speedy or rapid. So they have really rapid transmission. So from this point, it rapidly travels down either side of the septum. The septum is called the interventricular septum because it separates the ventricles. The right bundle depolarizes the right ventricle, and the left will depolarize the left ventricle and the interventricular septum. So both bundle branches terminate in the Purkinje fibers. And there's a little diagram that zooms in closer, halfway up on the right-hand side. The Purkinje fibers are the smallest, and they are located throughout the myocardium. So when the impulses reach the HIS Purkinjean system, they travel to the papillary muscle. Contractions precede that of the ventricles. So this is important so that there's not any regurgitation of blood flow through the AV valves. So you'll notice on the slide that these pathways are marked in yellow to make it easier for you to follow. Okay, the next slide gives a good overview of the electrical current leaving the cells of the SA node. If you'll note, the intercalated discs with the gap junctions. Remember back when we talked about the striations in the skeletal muscles and the heart muscle tissue, what their appearance looked like. On the top, you will see what the action potential of an autorhythmic cell looks like, remembering these are also called pacemaker cells. Then further to the right, you'll see the membrane potential of the contractile cell. And you can compare what those two potentials look like. So the top one is the membrane potential of the autorhythmic, that's hard to say, autorhythmic cell, and the one further to the right is the membrane potential of the contractile cell. So now that we understand some of the physiology, we can look further into the action potential. The membrane potential is always in millivolts with the time across the bottom of the chart. So there are 5 phases that always start and end in the 4th phase. So when you look at the chart, phase 4 is in the resting potential, and that's always somewhere around a negative 90 millivolts. When the chart spikes upward, this is what we call depolarization, and it's followed by a brief repolarization, then a plateau, and that's what's different. And finally, a repolarization that leads back down to the resting potential. So we can look more in depth at what happens in each phase of the action potential of the cardiac muscle. So the phases are numbered 0 through 4, but we start with 4, then we go 0, 1, 2, 3, and back to 4. So phase 4 is your resting potential. Phase 0 is the depolarization. Phase 1 is early repolarization. Phase 2 is your plateau. Phase 3 is the repolarization. And in phase 4, the resting potential again, where the sodium and the calcium channels are closed. So phase 0, this is where the action potential is triggered. Fast sodium channels start to open up one at a time. So sodium leaks into the cell, raising the transmembrane potential to around a negative 70 millivolts, which is a threshold potential. Each fast sodium channels have opened, generating a self-sustaining inward sodium channel. The large sodium current quickly depolarizes to 0 millivolts. Then the fast sodium channels will close as they are time dependent. The L-type long opening calcium channels open when the membrane potential is greater than a negative 40 millivolts. So creating a small steady influx of calcium down the concentration gradient. Now we move on to phase 1. The repolarization of the transmembrane potential is slightly positive. So some potassium channels are open briefly, and outward flow of potassium will return to 0 millivolt potential. In phase 2, the L-type calcium channels are still open with a small inward current of calcium. Potassium leaks down the concentration gradient through delayed rectifier potassium channels. These two counter currents are electronically balanced, and the transmembrane potential is maintained at plateau below 0 millivolts through this phase. Okay, now let's look at phase 3. It's the repolarization, and the calcium channels are gradually inactivated. The constant outflow of potassium now exceeds the calcium inflow. And this will bring the transmembrane potential back down to resting potential. The normal transmembrane ionic concentration gradients are restored when the sodium and the calcium ions are returned to the extracellular environment and potassium ions to the insides of the cell. So the pumps involved are your sarcolemma sodium-calcium exchanger, the calcium ATPase, and the sodium potassium ATPase. So now we're back to phase 4, the resting potential, and the process starts all over again. So if we just wanted to do a really quick generalized summary, we would start with, we have 2 types of cells in the myocardium. We've got the contractile and the non-contractile. And we said the contractile make up about 99% and the non make up that other 1%. The non-contractile results in the initiation of the action potential, and the contractile do the mechanical work of pumping the blood through the heart to the body. So within the autorhythmic non-contractile cells, remember that's your 1%, is something called a pacemaker potential that describes changes in the ion environment. And this is a unique behavior, and these channels have been given the name funny channels. When one action potential ends, a funny channel opens. Cardiac tissues are the only place that this will happen. The action potential starts in the SA node, and the phase goes from 4 to 0, 1, 2, 3, and then it starts all over again at resting potential of 4 again. So here's a question I want you to think about. Tetanus affects skeletal muscles, but not cardiac muscles. So how do you think this would affect the cardiac muscles? How do we think that tetanus would affect the cardiac muscles? Give you some time to think on that and have discussion. And these are the works that I cited for this video. Thank you.